In this class, we will discuss about basis and dimension. This class is divided into 3 sessions. First session deals with the introduction, second session deals with the basis existence theorem, and third session deals with the basis extension theorem. Before going to the definition of basis, let me recall two terms, linear independence and linear span. Let V be a vector space over a field F. S is linearly independent means when the linear combination of the elements of S equal to 0, if all scalars are equal to 0, then S is called linearly independent. That is A1 alpha 1 plus A2 alpha 2 plus so on A n alpha n equal to 0 implies A1 equal to A2 equal to so on A n equal to 0, provided S equal to set of alpha 1 alpha 2 alpha n. A linear span of S means that is the set of all possible linear combinations of the elements of S. Now, basis means that is a subset of a vector space which satisfies two conditions. First one is that is linearly independent, second one is that spans V. Best example for the basis is, first of all, consider the vector space C of R, where C stands for complex number system and R stands for real number system. Usually every complex number can be expressed as A plus B I, where A comma B are real numbers. We can rewrite it as A into 1 comma I. That means this spans C, and also we know that this is linearly independent subset of C of R. So, we can say that this is a basis for C of R. Another examples are the standard basis S equal to 1 0 0, 0 1 0 and 0 0 1, which is the basis of you can say R cube of R. Another example for basis is S equal to set of 1 comma x square so on x power n so on. This is a basis of the vector space V of f of x over the field F. From this we can notice that a basis may not be finite every time, that could be infinite also. Now, we will discuss a problem related to the basis. Let S equal to set of 1 0 0 1 1 0 1 1 1. We want to show that this is a basis of C cube of C. Before doing this problem, we remember one thing, that it is whenever we want to prove L of S equal to V, usually we prove L of S is a subset of V and V is a subset of L of S. But as we are taking S as a subset of V every time, this is always there, L of S is a subset of V. So, only thing we need to prove is V is a subset of L of S. That means every element of V is a linear combination of the elements of S. Now, come to the problem. Here we need to show that S is a basis of C cube of C, means we need to prove two things. One is S is linearly independent, another one is L of S equal to C cube. That means every element of C cube is a linear combination of the elements of S. So, first we will prove the linear independence. For that, take the linear combination of the elements of S as 0. And see whether all scalars are equal to 0. If it is true, then we can say S is linearly independent, but this implies a plus b plus c comma b plus c comma c, this is equal to 0 0 0. That means we can write it as c equal to 0, b equal to 0. Of course, b plus c equal to 0, a plus b plus c equal to 0. So that means b equal to 0, c equal to 0, b equal to 0, a equal to 0. Means when the linear combination of the elements of S equal to 0, then all scalars are equal to 0. That means S is linearly independent. Now we prove the remaining point, that it is every element of C cube is a linear combination of elements of S. Let us take an element in C cube and write it as a into 1 0 0 plus b into 1 1 0 and c into 1 1 1. XYZ is a linear combination of the elements of S, means here we need to show that A, B, C are nothing but the values of x, y, z, means we need to prove that A, B, C are the values in terms of x and y and z. From this we can write x, y, z equal to a plus b plus c, b plus c and c. From this we can write c equal to z, b plus c equal to y, a plus b plus c equal to x. That means c equal to z, b equal to y minus c, a equal to x minus b minus c. That means c equal to z, b equal to y minus z, a equal to x minus of y minus z minus z. That implies c equal to z, b equal to y minus z, a equal to x minus z. So now we can express x, y, z as x minus y into 1 0 0 plus y minus z into 1 1 0 plus z into 1 1 1. We know that x, y, z all are belongs to C. That means x minus y, y minus z are also elements of C. Means now we have expressed a triad in C cube, that means x, y, z as a linear combination of 1 0 0, 1 1 0, 1 1 1. That means we can express any element of C cube in this manner. That means S spans C cube. That means L of S equal to C cube. So now we can declare that S is the basis of C cube of C. By using this condition, now we can find the coordinates of any element of C cube. Say for example, take the element as 3 plus 4i, 6i, 3 plus 7i. As we know that x, y, z equal to x minus y into 1 0 0, y minus z into 1 1 0, z into 1 1 1. Just replace x by 3 plus 4i, y by 6i, z by 3 plus 7i. Means here we can write it as 3 plus 4i minus 6i into 1 0 0 plus y minus z, means 6i minus of 3 plus 7i into 1 1 0 plus z1, z means 3 plus 7i into 1 1 1. That means this is nothing but 3 minus 2i into 1 0 0, and this is minus 3 minus I into 1 1 0 plus 3 plus 7i into 1 1 1. So the coordinates of 3 plus 4i, 6i, 3 plus 7i with respect to the basis S are 3 minus 2i minus 3 minus I and 3 plus 7i. So in this session we have discussed about the definition of basis and some examples related to basis and one problem related to basis, and we have solved one problem related to the finding the coordinates of the elements of CQ. Finite dimensional space. A vector space V of f is said to be finite dimensional if there is a finite subset S in V such that L of S equal to V. That means which has a finite spanning set, that is called a finite dimensional space. And now we are going to prove a theorem related to, you can say, that is a basis existence theorem. The statement for it is, if V of f is a finite dimensional vector space, then there exists a basis set of V. Before proving this theorem, let me recall one result related to linear dependence. Let S equal to set of alpha 1, alpha 2, alpha n be a subset of a vector space V of f. Then S is linearly dependent if and only if some element in S, say alpha k, where k lies between 2 and n, can be expressed as a linear combination of its preceding vectors. This is very important result in proving this theorem. Now come to the proof. Consider a finite dimensional vector space V of f. Finite dimensional vector space means that has a finite spanning set, means that has a subset which is that has a finite subset which spans V. Then there exists a finite set, okay, you can say finite subset S of V such that L of S equal to V, and take S as set of alpha 1, alpha 2, alpha n. We are going to prove that S provides a basis, means already that spans V, only thing left is independency. If S is linearly independent, then we are through, means we got a required basis. Otherwise means suppose S is linearly dependent, then we have to search for a set which is both linearly independent and spans V. But already I have written one result before this one, that which says that whenever a set is linearly dependent, then there exists an element in that set which can be expressed as a linear combination of its preceding vectors. So, by using that result we can say there exists an element, say it is alpha I in S, which can be expressed as a linear combination of its preceding vectors. That means alpha I can be expressed as a1 alpha 1 plus a2 alpha 2 plus so on a I minus 1 alpha I minus 1. Now, construct a set S1 with the exclusion of alpha I from S, that means S1 equal to S minus alpha I. That means S1 is nothing but alpha 1, alpha 2, alpha I minus 1, alpha I plus 1, so on alpha n. Since L of S equal to V, obviously L of S1 equal to V. Here is the proof for it. Let alpha belongs to V. We know that L of S equal to V. That means every element in V can be expressed as linear combination of elements of S. That means alpha equal to B1 alpha 1 plus B2 alpha 2 plus so on B I minus 1 alpha I minus 1 plus B I alpha I plus B I plus 1 alpha I plus 1 plus so on B n alpha n, where all scalars belongs to field F. But we know that alpha is a linear combination of alpha 1 alpha 2 alpha I minus 1. Just substitute that here, then we get alpha equal to B1 alpha 1 plus so on B I minus 1 alpha I minus 1 plus B I into A1 alpha 1 plus A2 alpha 2 plus so on A I minus 1 alpha I minus 1 plus B I plus 1 into alpha I plus 1, so on B n alpha n. That means alpha is equal to B1 plus Bi into A1 into alpha 1, because both are having alpha 1 common element, plus B2 plus Bi into A2 into alpha 2 plus so on plus B I minus 1 B I into A I minus 1 alpha I minus 1 plus plus B I minus 1 into alpha I minus 1 plus next term will be B I plus 1 alpha I plus 1, next term B I plus 2 alpha I plus 2 plus so on B n alpha n. That means alpha is a linear combination of alpha 1 alpha 2 alpha I minus 1 alpha I plus 1 and alpha n. That means alpha is a linear combination of the elements of S1. That means we can write L of S1 equal to V. So, our new constructing set spans V. If this is linearly independent, then we are through. That means we got our basis. If not, again we construct a set S2 with the exclusion of one element which is a linear combination of the preceding vectors in S1. If we continue this process after finite number of steps, definitely we will get a subset of V, say it as Sk, which satisfies two conditions. One is L of Sk equal to V, and another one is that Sk is linearly independent. And do remember, the least possibility for Sk is a singleton element, say it is alpha k. And at the beginning of this theorem, I forgot to tell one thing, that it is we have considered a set S with all non-zero elements. So, here if we end up with a set with only one element and it is, as it is non-zero element, this is always linearly independent. That means finally we can get a basis for a vector space V of f. That means every finite dimensional vector space has a basis, of course that is a finite basis. So, from this from now onwards we can say whenever we have a finite dimensional vector space, then we can declare that it has a finite basis. Now, we can go to the definition dimension. Dimension means nothing but that is the number of elements of in any basis of a finite dimensional vector space. We already mentioned that each finite dimensional vector space has a finite basis. So, best examples are here. Already we knew that 1 comma I is the basis of C of R. That means dimension of C over R is equal to 2. And also this is the simple basis for the vector space of a real number system over a real number system, singleton 1. That means dimension of R over R is equal to 1. So, in this manner we can we can write many dimensions of vector space. Say for example, we can directly write like this: dimension of R power n over R is equal to n, where R power n stands for n dimensional vector space. If we take 2, that is a 2 dimensional vector space, and the standard basis for it is for n equal to 2, the standard basis for it is 1 0 0 1, n equal to 3, the standard basis is 1 0 0 0 1 0 and 0 0 1. As we already mentioned that examples for basis, from these examples we can say that there is an infinite dimensional vector space also. The second example shows that that is an infinite basis of the vector space over there. So, in this class we have discussed about finite dimensional vector space definition and the basis existence theorem. Basis extension theorem. That means every independent set is itself a basis of V, or it can be extended to form a basis of V. Before proving this theorem, let me recall one result, that it is that is called linear independent lemma. If alpha 1, alpha 2, alpha n is linearly independent, in V of f, and alpha does not belongs to span of alpha 1, alpha 2, alpha n, then set of alpha 1, alpha 2, alpha n comma alpha, this is also linearly independent. Proof is simple. We can rewrite the previous result. We can rewrite our known theorem. Means our known theorem is this one. A set S equal to set of alpha 1, alpha 2, alpha n is linearly dependent if and only if there exists an element alpha k, where k lies between 2 and n in S, such that alpha k can be expressed as a linear combination of its preceding vectors. So, you can say this is a consequence of this theorem, or else you can say this is the contrapositive of this theorem. So, by using this result we can easily prove the basis extension theorem. Proof: consider a vector space V of f. Of course, consider a finite dimensional vector space V of f, and S equal to alpha 1, alpha 2, alpha m, which is a subset of V of f. Of course, which is a linear independent subset of V of f. We need to prove that S is itself a basis, or it can be extended to form a basis. So, to prove that S is a basis, only thing left is L of S equal to V. So, if it is true in this case, then clearly S is itself a basis. Otherwise means L of S not equal to V. L of S not equal to V means L of S is a proper subset of V. That means there exists an element alpha 1 in V such that alpha 1 does not belongs to L of S. This tells us that alpha 1 is not a linear combination of the elements of S, as our previous already mentioned result says that S union alpha 1, this is clearly linearly independent, because we already assumed that S is linearly independent. If this one, say this is S 1, if L of S 1 is equal to V, then we are through. That means this is our required basis. If not, again we do the same thing, that it is L of S 1 not equal to V, that means L of S 1 is a proper subset of V. That means there exists an element in V which is not in L of S 1. Say it is alpha 2. Again we can construct a set S 2 which is nothing but S 1 union alpha 2. Of course, as our result mentioned says that this is always linearly independent. Again if L of S2 equal to V, then we are through. Otherwise, if we continue this procedure, as we are dealing with the finite dimensional vector space, means it has definitely a finite basis. That means we end up with a finite set, say it is Sk, which is both linearly independent and L of Sk equal to V. That means we started with S. If it is a basis, it is okay, otherwise we have extended it to form a basis. So, this is what basis extension theorem says. Now, we will look at a beautiful application of the basis extension theorem. For any finite dimensional vector space, any two bases have same number of elements. For example, we already seen this thing 1 0 0 0 1 0 0 0 1. This is a basis of R cube of R. You can say that is a standard basis, and in this class we have proved that 1 0 0 1 1 0 1 1 1, this is also a basis of this is a basis of C cube of C, but this does not matter whether we take R or C here. So, just for our convenience, take this as C cube of C. That means these two are bases of C cube of C, but notice one thing, that it is this consists of 3 elements and also this one. That means a vector space may have n number of bases, but the number of elements in those bases are same. Now, we are going to prove the same by using basis extension theorem. Consider a finite dimensional vector space V of f and assume V of f is having two bases, say S1 and S2. Take S1 as alpha 1, alpha 2, alpha n, and S2 as beta 1, beta 2, beta m. If we prove n equal to m, then our task will be over. That means the number of elements of two bases is same, but these two are numbers. Numbers, how to prove two numbers are equal means there are two ways. One is using division. If m divides n and then n divides m, then m equal to n. Otherwise, m less than or equal to n, n less than or equal to m equal to n. Of course, both are same. When we say m divides n, that means m less than or equal to n divides m means n less than or equal to m. So, now we take this one, m less than or equal to n less than or equal to m implies m equal to n. But how to reach these two? That what basis extension theorem shows. So, S1 here, that has n number of elements, and S2 has m number of elements. So, first of all, treat this as a basis, as it is basis of V of f, and treat to S2 as only linearly independent set, because basis means that satisfies two conditions. One is linearly independent, another one is that spans V. So, just take only one condition from that it is S2 is linearly independent. But our basis extension theorem says that every linearly independent set is itself a basis or it can be extended to form a basis. So, from that by using the theorem we can find a relation, we can form a relation between M and N, as S2 consists of M elements and S1 consists of N elements. M is always less than or equal to N, say this is 1. And now treat S2 as it is, means S2 is a basis of V of f, and now treat S1 as a linearly independent set. Again, by using basis extension theorem, here we can form a relation that n less than or equal to m, because the number of elements in S1 is n and the number of elements in S2 is m. Here we are considering S1 as a linearly independent set. That means S1 is itself a basis, or it can be extended to form a basis. That means the number of elements in S1 is always less than or equal to the number of elements in a basis. That means n less than or equal to m. So, from 1 and 2 we can declare that m equal to n. That means a vector space may have different bases, but the number of elements in those bases are same. So, in this class, in this session we have discussed about the application of basis extension theorem, and also there are more applications. Regarding dimension, one of them is assume V of f and U of f are finite dimensional vector spaces then dimension U equal to dimension V if and only if there is an isomorphism between V and U. With this, I am closing this session. Thank you all.